Hello, greetings. Well, that is too enthusiastic. Well, we are rambling. We are still looking at the department's paper one from May 2023. Almost at the end. Two more questions to go. So today we're looking at 10.2. Let's go. Three events A, B, and C are considered. The probability of A is 2/5. The probability of B is 1/4. The probability of A or B happening is 13/20. So, first question is, are events A and B mutually exclusive? Support your answer with the necessary calculations. Okay, mutually exclusive are events where there is zero chance of them happening at once. So, if A and B are in fact mutually exclusive, then we will expect the sum of the probability of A and the probability of B to be the same as the probability of either of them happening. Because, so if you think about events where there is an overlap, right? So suppose we had event M and event N, and the chances of M happening is 1/2, and the chances of N happening is 1/4. If you just add up the probability of M and the probability of N and say that that's the probability of either of them happening, what you're doing is you're counting this little piece that falls under M and falls under N. You're counting it twice. So you're actually inflating the chances of either M or N happening. So but if your events are mutually exclusive, then you don't have to worry about double counting. You can just add the probability of this and the probability of this, and that would give you the probability of either of them happening. Okay, so what we are looking for is the sum of the probability of A and the probability of B the same as the probability of A or B happening? So let's do that. So for 10.2.1, we're going to calculate the probability of A plus the probability of B. So that is 2/5 plus 1/4, and I think 2/5 is 0.4. 1/4 is 0.25, so that comes to 0.65, which is 13/20, right? And we saw that the probability of A or B happening is also equal to 13/20, so that means there isn't an intersection between A and B. So therefore, the probability of, wait, what am I saying? So therefore, A and B are mutually exclusive because the probability of A plus the probability of B happening is equal to the probability of A or B happening. Okay, let us shrink that up. Okay, all right, next question. Determine the probability of only C happening if it is further given that the probability of A or C is 7/10, the probability of A and C is 2/5, and 2 times the probability of B and C is equal to the probability of A and C. Okay, so this is just algebra on steroids, but we are not afraid. So I'll just start by drawing myself a little Venn diagram. So we know that A and B are mutually exclusive, right? And then we've got C, who seems to be friends with everyone until proven otherwise. Okay, so we know that, let's see here. So I'm just going to temporarily call this X, right? We know that the probability over here is 2/5 minus X. So just this bit over here, excluding the intersection with C. Okay, and then what else do we know? If we call this one Y, right, this little piece over here, then we know that this outer part only be happening is 1/4 minus Y. So that would be this bit here. Okay, so all in all, this is a quarter and this is 2/5. Okay, right. What else do we know? So we also know that the probability of A or C happening is 7/10. Okay, so that's an interesting one. So this whole shadoodles here, do you see why it's so good to have colors in your exam? Like, please do not leave your coloring pencils behind. Okay, so that whole union, the probability is 7/10. And then the probability of A and C happening is 2/5. How interesting, because the probability of A is 2/5. So actually, A is not actually, there isn't a chance of only A happening. If A happens, C has to happen as well. So that changes our diagram slightly. So our A actually lives inside here, right? And so actually the probability of A or C happening is actually just the probability of C happening, because A is completely inside C. Right, so let's move that in here, and we know that this is 2/5. Okay, right. And so what we also know is this little bit over here okay, would just be the same as 7/10 minus this piece, right? Since the whole of C is 7/10, then the chances of only C happening, well, you can't really have, well, okay, I can't say only C happening. The chances of C happening but not B happening is 7/10 minus Y. Okay, anyway, wow, this is really getting me into knots. Right, and then we know that 2 times the probability of B and C. So that's our cute little Y over here. Right, so 2Y is equal to the probability of A and C happening, which is this, right? We know that, yeah, if A happens, C happens. All right, so that'll be 2/5. And so Y will be 1/5, right? And then we're asked, okay, what are the chances of only C happening? So we want this piece over here, excluding the A, excluding the B. What are the chances of just C happening? And so that would be the 7/10 minus this piece minus this. So that would be 7/10 minus the A, the chances of A happening, and minus the chances of B and C happening, which is 1/5. So that would be 0.7 minus 0.6, so that's 1/10. Right, so the probability of only C happening is 1/10. Wow. Okay, let's just double check that with the memo, because she's, man, making me sweat. Also, I don't want to carry on if I've gotten something wrong. Right, so first one agrees that the events are mutually exclusive, which is awesome. Then the second bit, we agree, it's 1/10. Ooh, wow, that was such an interesting exercise. Okay, I'm just going to try to write this out better. Is it worthwhile? No, I am not going to try to write it out better. I think as long as we got the gist of what was happening, we're good. I think the only strange thing was recognizing that the probability of A and C happening is the same as the probability of A happening. So the key thing to recognize there is it is not possible for A to happen without C happening, right? Because the probability of A happening is the same as the probability of A and C happening. So there isn't a chance that A could happen by itself. So when we draw a Venn diagram, the A has to be completely inside the C. And at the same time, we know that A and B don't intersect. So we're not having a situation where, we're not dealing with a situation like this, where A kind of goes into the B a little bit. Nope. Only C and B intersect. Okay, wow, that is interesting. So, the next question says, determine the probability that events A, B, or C do not take place. So we don't want any of them to happen. So we're trying to figure out the probability that we end up out here, outside of the circles, right? So, how do we work that out? Okay, so we know that the probability of A or B or C happening is going to be, so we know that C as a whole is 7/10, and then B is a quarter, but then we have to minus the intersection, which is the 1/5. Okay, and what does that come to? So that's 0.7 minus 0.2, so that's 0.5 plus a quarter, so that will be 3/4. Right, and so therefore the probability that none of them happen, so neither A nor B nor C happen, okay, the complement would be 1 minus that, okay, which is equal to a quarter. Right, and do we agree? Yes, we do agree. Awesome potatoes. Right, that wraps that video up. Very interesting question. Definitely can tell that we were heading towards the end of the exam. Right, let's go on to the last question in the next video.